Today we're going to see a summary of the different types of control systems and what each one does and what the role is of each in solving the different challenges that we have in controlling a system. So let's examine the two major divisions of controls, which are open loop control or closed loop control, and develop from there. Okay, so we have the control systems divided into closed loop and open loop systems. Let's look at some very basic concepts as to what we want to do. We want to use the computer to help us design controls. We would like to define what a control system is. Control system is a system whose purpose is to regulate or adjust the flow of energy to some level, some manner of a system that we already have. Closed loop systems uses measurements of an output, compares it to the desired value, and then corrects it. That's how a closed loop system works. Open loop system does not use feedback at all. Adjust the flow of energy according to some prescribed schedule. I think, as I was saying, the lights, for example, the program lights could be a perfect example of open loop systems. If you say you have a light that turns in at 6 o'clock, turns on at 6 o'clock and then turns off at 10, let's say it's a porch light, that is a perfect example of an open loop system. There's in between 6 and 10 o'clock, there's no feedback to or question is the light on or off. It's pre-programmed one time, uh, flip the switch on or off as open loop system, open loop control. Automatic controls. Automatic control is one that acts without any outside intervention from a manual system that requires an operator. It, automatic controls could be either open or closed loop system. I just described you a system. If you turn on the lights at 6 and turn them off at 10, this could be done automatically. Every time that the clock hits 6, it will turn on. You can program them even by the days of the week, some of the switches. Same way the sprinklers work exactly like this too. Uh, and that's an automatic system. So what we're going to do is to, using computer models, study the systems and their controls. This is a overall view of the control system with the possible uh, attachments or possible changes that may occur. Your system is this one, this G1. I want to explain to you every single block that you see here. You may say, well, Professor, this looks like a very complex system. It's not just a simple control. True. But this is about as complex as you're going to get it. So what we're going to see is that this is your system. This is what we've been studying so far, doing models of the physical system. You measure something, and that measure is some sort of analytical measure of a physical variable, let's say speed. This transform into a voltage. And depending on that, this is the reference, R for reference, and the difference between the reference and the feedback signal all these things have to be in, this is an electrical part. So the difference you you will have to correct. And this at this point, that's what these blocks are doing. They are correcting what the feedback is telling us to do. So that way, this is the single. This is the feedback control with other attachments, you may say. But the basic idea is the system feedback control reference produces an error, and then the error corrects it. But you see, let's say that before your correction gets to the system, let's see, if you're trying to keep the temperature of the room constant, and then somebody opens the door and cold air comes out. So that's called a disturbance, and that's represented here. So the disturbance acts, here's your control that is trying to compensate, and then that compensated input goes into the system, and then you have the same loop again. That's how this goes. Okay. So now we are going to see a bit about control laws. If you take a step input to a system, you study how it responds, you will see that the system, you can recognize several properties, you may say, like for example, the maximum overshoot is over here, and then it would settle down into some steady state value, which I told you that this measure from the steady state response to the original system. This is called the steady state error. So obviously, one objective that we have is how do we minimize the steady state error? How do we set it? How do we make it zero so that the response would be totally accurate? That's what we need to do. So in this particular case, our objective is to minimize the steady state error, to minimize the settling time. We have in here the peak time to the maximum, and this would be the settling time here we measure here. Um, then we need to look at some response to to minimize the maximum overshoot and other desired conditions that we want to change. So you have like a two-position control, proportional control, you have integral control, and then you have derivative control. Okay? So if we look at this, we have the two-position control is just like the on and off switch. The proportional control is the more error that exists, the more control I'm going to give. So the control system is proportional to the error. So this is the difference between the input and the feedback, or the difference between the reference point and the feedback. That's what we need to correct. So that if that error exists, what what this method does is the bigger the error, the more control. That's why it's called proportional. Then you have another type of controller, which instead of being proportional to the error, it depends on the integral of the error. Uh, is proportional to the integral of the error. If you have the derivative form, then this is proportional to the derivative of the error. And so our job is to study each one of these. The two-position control system, as you can see, what we have to do here is you take value in time and then turns on, goes back in a loop. Okay. In this case, the control output is determined by the magnitude of the error. So you see that the error is R minus C. R is the set point, C is the control variable, F is the control signal. So you will have the error here. All right. Let's take a look in here, for example, a liquid level control system. This is like on and off reaction. Okay. This is the control level of a tank. Depends on how much water it comes in. It fills the tank, and this thing is going to either close the circuit or open it. But there are several ways of making this happen, but a common way is to have just a control in here. Either this is floating or not, depending on what the level of that tank is. So you can see here on the right hand side, we can examine this, and you see there's the time, and then there is the switching in here. This is the real behavior with a little bit of overshoot or undershoot. So this is the kind of response that we should get from an on and off controller. The bang controller goes from negative to positive, as you can see here. It follows this characteristic. You have an example in here with a ideal bang controller, the one on A, and the one on B is not perfect bang controller. It has some gap in there, some dead zone. Okay, let's take a look at this. This is a temperature controller. Okay, this reminds me of Thanksgiving, right? Turkey time, you put it in the oven, it needs to be a certain temperature for a certain amount of time. So in here, you go in, and then this is the heating element. Turkey is inside. You sense what the temperature is. And depending on this, either this potentiometer allows more current to flow here. Okay, and then this heats up after a certain time. You do this thing again. Compare the set point with what you're getting and adjust the temperature, meaning it's the oven will go on or go off depending on what it needs. Okay. And these are the simple control loop equations that we can have. We start with the simple equation of the system. So we always have to have a physical system. And then we define the control condition. You say if T2 is constant, then the heater is the same as the input. I mean the heater will track what the input is. So Q of the heater would be Q, the amount of heat. It would be equal to the amount uh, that you need. No? Like for example, the steady state Q would be the 200 minus 70 degrees, which are the two temperatures, divided by R2. The amplifier circuit function, this has the ability to put voltage in or not. So you will have that the heater output would be Q of steady state plus M. And then you have M would be a constant times the error. Yeah. K1 and K sub 2 are the scale factors of the potentiometer, and M is going to be the heat necessary to control this. If you have like a temperature deviation T2 is 200 degree and T0 is 70 degrees. So you can see that you make the difference. You say the error is Q minus Q of a steady state. Okay. This you can see now the system with some more blocks in here that we need to recognize. You have your system over here, and this is your measurement. You feed back your measurement to a reference point, like in here too. Think of it, this would be like the box, your regular temperature of the dial on the oven. That position needs to be transformed into an electrical signal through this. And that electrical signal, compared to what you get of the feedback, you get the error. In this case, deliberately, we are making the correction with proportional control, just with a constant. And what you see on the left-hand side are the disturbances that we need to account when we design controls. So you will see this is trying to control, and then this in here it creates a disturbance. Okay, what are the design parameters? These are the ones that you have studied I believe on chapter 4 we touched on this. What is the time constant? What's the damping ratio? What's the natural frequency of the system? Is it stable, not stable? Is it accurate, not accurate? Is it fast or slow? All these things are kinds of changes that we can do. Let's do an example of a position control system, which this obviously is a closed loop system. Okay, so take a look at the top picture. You have your motor here. The motor is going to produce a speed, angular velocity in this case. In industry, they call it rate. First time I heard that term, I said, what does exactly they mean? They mean the angular velocity, right? And so the angular velocity there is measured, and you can see here's the measuring device. It's just like measuring the speed of your car by looking at the transmission gear or the motor gears, and I'm measuring how many RPM it's doing. So depending on that, you have this feedback that goes back here to compared with with this power amplifier here, or power regulator, you may say, and then you have the motor torque, which with control the speed of our device in here. So that's how this works. Now in here, if you look, and of course this is a disturbance, meaning something external that messed up the control. We have to account for all that. So you have the system here. As you can see, the system is a transfer function. And then you have the feedback, the comparison here, and we have the controller here. Okay, that's how this works. So once we have a block diagram like this, the author on chapter 5, he talks about how you might want to reduce the blocks into simpler blocks. In many occasions, you don't need to simplify it to that level, but rather operate with the system itself and its control. Proportional control. This means the feedback signal is proportional to the error signal. So the more error, the more control. But you see, that not necessarily will produce the best answer. That's why we have other types of controllers. So in this case, also this has a steady state error. So it needs help. It needs to be compensated. But in a proportional control system, for example, you have this the differential equation of the system. You have both of them in there. And then you have the control law, which would be the torque would be proportional to the current. Okay. This is the way we would write the control system by establishing the difference between the set point and the error. This, again, keeping another example of a proportional control. This is measuring the angular rate or angular velocity and correcting it accordingly. So you measure this in here. This transforms it into an electrical signal and compare the other electrical signal with this here. So these little blocks, these are like analog to digital conversion. A lot of devices are like that. They measure a physical variable, but their output is a digital one. The temperature meters work like that. Speed control systems work like that. So if you make a simplified block diagram of what you have the system, you have the feedback, and you have the reference point here, and the, the controller is influenced a lot by this block. That's the one that can be proportional, integral, or derivative. So if you hear something like PID controller, that's what it means. It means uh, a controller that is proportional to the error. That is the proportional control. Okay, typical transfer function, if we change in the speed, we could put a step input for an input and get the output. Remember the transfer function, this transfer function is going to be k times the transfer functions in the absence of a disturbance, right? But let's assume we don't have the disturbance, but the transfer function of the position with respect to um, the input is this, or this with respect to the torque. If we put a step input, it's like we multiply by 1 over s. You can use, you're going to find it on your text, the ability to do partial fraction expansion, but we don't really need to. But if you do, would be the way we set up the problem. The final value is less than 1, but close enough if E is small. And then at the bottom of the slide, you can see this comment that the time required to reach this value is approximate 4 time constants. So that's what proportional control is. We can study the, like you say, the system times the step input, or using the final value theorem, find out the steady state effect. Proportional controls are as good for first order systems. The output never reaches desired value. If resistance is present, which is the case like on driving a vehicle, though it can be made arbitrarily close by choosing the gain k large enough, this is called the offset error. The output approaches the final value without oscillation. The time to reach this value is inversely proportional to k. Obviously, because remember I said the more error, the more control. So it's going to react quickly at making it proportional to the error. These are the properties of order systems under proportional control. The deviation due to the disturbance at the steady state is inversely proportional to the gain. Gain is another word that is used for the control constant. So it always has an error. This is a drawback of the proportional control. So let's just stop for now on the proportional control, and we'll continue with the integral control in another video.